Hi guys, welcome to lecture number 7 of the Basics of Mechanics lecture series, where I'm teaching the fundamental concepts of engineering mechanics. Today's the day we're gonna learn about moment of inertia. To be more specific, we're gonna learn about area moment of inertia. You might have noticed that the cross section of the rails used to construct railway tracks looks like eye in shape. In mechanics, we call it as I section. Now, there is a reason for this. You can ask, why can't the cross section be a rectangle or a circular cross section? And why is it an eye? The answer to that question is that an eye cross section has greater area moment of inertia than other cross sections. To know what is an area moment of inertia, let's move on to the next section. Assume that I have a beam and I'm placing some weight on it. Now, as I place the weight or as I apply some load, the beam might tend to deflect from its original shape. In such a scenario, depending on the cross section of the beam, there will be a certain resistance to the beam bending. A quantified measure of this resistance provided by the beam against its deflection or bending is called as area moment of inertia. You can also understand area moment of inertia as how the material is distributed across the cross section of a beam from its bending axis. In general, more the material away from the bending axis, more the resistance to the bending will be. As you can see, in I section, a large fraction of the cross section is at the maximum distance away from the centroid of the I section. Such a cross section provides large area moment of inertia and have a good resistance to the bending. Let's move ahead and derive the area moment of inertia for an arbitrary cross section. I have here an arbitrary cross section A, and let me assume that the bending or the deformation occurs with respect to my reference axis x. Now the idea is that if I consider an infinitesimal area from the entire cross section dA at a distance y from my reference axis, so this is my dA and this is at a distance of y from my reference axis, then the area moment of inertia is the total sum of all the resistance provided by all the infinitesimal small areas dAs throughout the cross section. This can be simply done by integrating y square over dA, or rather over the entire cross section. If you're thinking why we integrate y square instead of y, it's because one y represent the distance between the reference axis and the dA, while the other represent the local strain. During deformation, the local strain developed at dA is linearly dependent on the distance from the reference axis, which is y in this case. And hence we have to integrate y square instead of y over the entire area of the cross section. If we do that, we would be successfully calculating the moment of inertia along x-axis. So I of x will be equal to integration of y square dA over the entire cross section A. To calculate the moment of inertia along y-axis, we have to repeat the step by considering the distance between dA and the reference y-axis. So if the difference between the reference y-axis and dA is x, then we would have Iy is equal to integral of x square dA over A. So that's how easy it is to derive a moment of inertia for any given surface. Let's now move on to an example and try to implement this integral to come up with a formula for calculating the moment of inertia for a rectangular cross section. Alright, so I have a rectangular cross section with height h and breadth b, and my reference axis x and y pass through the centroid of the section. For deriving the formula for moment of inertia, we would need to consider an infinitesimal small area. So for that, I have considered a small strip with height dy, such that height times dy will give me the overall cross section area of the rectangle. Now the first step is to calculate dA. And as I said, dA in this case is a small strip with height dy and breadth b, so the area dA would be b times dy. From previous section we know the moment of inertia along x-axis is given by integral over the cross-section area of y square times dA. Now we need to apply the limits for our integral. Since the reference axis passed through the centroid and we are integrating over the height of the rectangle, we can set lower limit as minus h divided by 2 and upper limit as plus h divided by 2. When we substitute dA in the equation, we get Ix is equal to integral of y square b times dy within the limits of minus h divided by 2 to h divided by 2. Breadth of the rectangle is constant, so integrating y square with respect to dy, we have ix is equal to bh cube divided by 12. To calculate the iy, the moment of inertia along y-axis, we can simply exchange breadth and height. Then we will have iy is equal to hb cube divided by 12. Now these are the moment of inertia of the rectangular cross section along x and y axis respectively. Let's now try and derive the moment of inertia for the same rectangular cross section but with a different reference axis. Here I have my reference axis at the bottom edge of the rectangle. Again, the small area under consideration dA is b times dy and ix is given by integral over y square dA between the limits 0 to h. Since the reference axis is at the edge of the section, we need to integrate the integral between 0 to height h. Substituting dA in the integral and solving for ix, we get bh cube divided by 3. Similarly, when you derive iy, you would get iy is equal to hb cube divided by 3. Right. Now you notice that we have derived two different moment of inertia for same rectangular cross section. When the reference axis passed through the centroid of the cross section, we got bh cube divided by 2 as the moment of inertia along x-axis. But here, when the reference axis is along the edge, we have a different moment of inertia. Which one of these is correct? Well, actually, both the answers are correct. When calculating moment of inertia, it is very important to consider the influence of the reference axis of the deformation or bending. For more complex sections such as T or I, it is possible that the bending axis is not passing exactly at the centroid of the cross section. So for such a case, we need to be in a position to calculate the moment of inertia with respect to any reference axis away from the centroid. Moment of inertia along the centroid axis for usual cross sections such as circular, triangular or others are very much available in textbooks and internet. But to calculate the moment of inertia for any given axis, we can make use of parallel axis theorem. In the next section, we will discuss the parallel axis theorem with an example. To explain parallel axis theorem, let's consider our 2D mechanics potato. The centroidal x-axis is xc and the reference axis with respect to which we want to find our moment of inertia is represented as x. If the distance between two axes is d, then according to parallel axis theorem, the moment of inertia with respect to x-axis ix is equal to sum of moment of inertia with respect to the centroidal x-axis ixc and the product of area and the square of the distance d. So given the distance between the reference axis and the centroidal axis and the moment of inertia with respect to the centroidal axis and the area of cross section, we can calculate the moment of inertia with respect to any given axis using this theorem. Let us apply this theorem to the previous example where we consider the reference axis along the edge of the rectangle, and let's see whether we get the same answer as before. So here is our rectangle, and according to parallel axis theorem, we have Ix is equal to Ixc plus AD square. We know that Ixc is equal to bh cube divided by 12. Again, the moment of inertia along the centroidal axis is available all over the internet and in mechanics textbooks. The area of the cross section is b times h. Before finding the perpendicular distance between the reference axis and the centroidal axis, let's first draw our centroidal axis. Now we know that the centroid of the rectangle is exactly at the half of its height, so from the edge, the distance to the centroidal axis is h divided by 2. Substituting this in our parallel axis theorem equation and solving for Ix, we will get Ix is equal to bh cube divided by 3. This is exactly what we got in the previous section without applying the parallel axis theorem, and with this we now have proved that the parallel axis theorem works, haven't we? You can also try to solve for Iy, the moment of inertia along the reference y-axis using parallel axis theorem, and check whether you can get Iy is equal to hb cube divided by 3. Now before we end the video, there is one last topic to cover. We just saw that the area moment of inertia along x and y axis resists bending deflection. Now what if I want to twist the beam along z axis like this? Well, even in that case, there will be a resistance against this torsion from the cross section. This resistance to the torsional deflection is called as polar moment of inertia. To calculate polar moment of inertia, we will need to understand perpendicular axis theorem. According to perpendicular axis theorem, the polar moment of inertia along the z-axis, which is usually represented as Iz or J, is equal to the sum of moment of inertia along x and y-axis. From previous section, we know what Ix and Iy are, and when we add them both, we get the polar moment of inertia, which is J is equal to integral of x square plus y square times dA over the cross section. Now let's quickly apply the perpendicular axis theorem to our rectangular cross section. In this example, we are going to calculate the polar moment of inertia with Ix and Iy calculated along the centroidal axis. So Ix with respect to the centroidal axis will be equal to bh cube divided by 12, and Iy will be equal to hb cube divided by 12. Adding these two, we will have our polar moment of inertia J is equal to bh divided by 12 times h square plus b square. So with that, I conclude the lecture for today. I hope you enjoyed the video. If so, give me a thumbs up. This will encourage me to do a lot more of these lectures, and also consider subscribing to the channel. I will meet you guys soon in the next lecture. Until then, bye bye.